In this section, I'm going to talk about hybrid vehicles, what they are, kind of briefly how they operate, and how they can contribute towards low carbon vehicle technologies. Okay, so talked about in the short term, improvements in internal combustion engines and the efficiency of those to reduce carbon dioxide. But in the medium term, hybridization is required, and there doesn't seem to be much doubt about that. But you need to kind of be aware of the headlines because they can be a bit misleading. So, for example, there's been a couple of articles recently. So, this one was from the Independent. So, Volvo to make only electric cars from 2019. But when you read their press release, okay, even though they said all electric, that again they were misleading themselves. What they actually said is that they were making the historic end of cars that only have an internal combustion engine. So there's still an internal combustion engine in there, it's just part of a hybrid system. And again, The Guardian, when they were reporting on the government's plans, saying Britain to ban the sale of all diesel and petrol car vans from 2040. But when you read what they actually said, it said the end of the sale of all new conventional petrol and diesel cars and vans. So despite the headlines from the press, internal combustion engines are going to be around for some time, but just not in the form that we're used to. It's just going to be part of a hybridized system. We're not going all electric just yet. We don't have the capacity to do that. But yeah, so we're going to have internal combustion engines, but as I say, in a hybrid format. But this is one of the kind of challenges that hybrid vehicles face over conventional diesel and gasoline, the ones that want to be banned. Is this shows a comparison of energy sources. So what we have on the side is the energy density. So this is the joules per litre, and on the bottom we have the specific energy. So this is joules per kilogram, and there's various different energy sources on here. So if we look at the incumbent fuels, if you like here, so gasoline and diesels, you can see that they have pretty high energy density and pretty good specific energy. So they have a lot of energy per kilogram and they're very dense, so they also have a lot of energy per litre. So they're very good fuels for carrying around with you if you need to spend energy as you go. In contrast, some of the other ones, so you look at the batteries, they aren't very good in terms of energy density or specific energy. Part of the reason why electric vehicles are struggling to increase their market share because of this range anxiety. You probably know that you can't go that far without the vehicles running out of charge. So not particularly good at the minute, but that could change. And also hydrogen, people talk about fuel cells and hydrogen powered vehicles. Yes, hydrogen has a very high specific energy, but because hydrogen isn't very dense, it doesn't have very good energy density. So you need vast volumes of it to be able to extract the energy that you need to travel on. So as I say, the incumbent fuels are kind of pretty good in terms of what you want. You want to be towards the top right hand corner of this plot, which is where they are. And then there's some kind of the fuels in the middle, such as ethanol and methanol. So that said, I think hybrids are going to become more and more prevalent. And there's many different types, and effectively what a hybrid vehicle is it's a vehicle that combines two modes of two prime movers, effectively two ways of powering the vehicle. So typically when we talk about, from a vehicle point of view, we talk about an internal combustion engine and an electric propulsion system. But there are other vehicles, so kind of subtypes of that. So we can have what's called a plug-in hybrid electric vehicle, where the battery is charged by connecting it to the main, so it kind of has the functionality of an all-electric combined with a hybrid electric vehicle. You can have what's called a range extender electric vehicle, so basically the engine is effectively running as a generator, which is producing electricity to power the vehicle to go forward. And essentially, each vehicle can be broken down into what's called either a parallel hybrid vehicle or a series hybrid vehicle. And we'll talk about both of these on the next couple of slides. So in terms of a series hybrid, so as the name suggests, the power is kind of in series. So in a series hybrid vehicle, only the electric motor mechanically drives the vehicle. Okay, and the internal combustion engine effectively acts as a generator, charging the batteries when required. You can see the fuel tank here, it's driving the engine. You've got the alternator, which then is managed by the ECU. So either that electricity could be used directly to drive the motor, or it could be used to charge the batteries. And if the batteries are sufficiently charged and the engine isn't needed, energy can be used from the batteries and through the drivetrain. The reason this can go back the other way is these vehicles are often fitted with regenerative braking, so that as you're braking, you're using this motor as a generator, so you can also generate electricity going back the other way. So you're recovering the energy from decelerating the vehicle. So say this is all going in series. In parallel, both power sources can drive the vehicle. So you can see that there's no direct charging of the batteries from the internal combustion engine here. So the fuel drives the engine, which can then drive the wheels. The motor is obviously then connected to the same transmission system, and the batteries can either be charged up, again with regenerative braking, or can be depleted through the motor to drive the wheels. And this can kind of, you can have kind of what are called mild hybrids. So you use quite a compact electric motor. And that might just be so rather than using the motor to actually drive the vehicle, at a sensible speed, they're just used for stop-start, so to turn the engine back over, power assist, and just regenerative braking. So I'll briefly talk about the advantages and disadvantages of each of those technologies, the series and the parallel. So in terms of a series, because only the electric motor is connected to the wheels, you have a much simpler transmission because it's only got to deal with one motor. It also allows the option for having one motor per wheel, so you could have all-wheel drive and kind of thrust vectoring as a result. So you could, torque vectoring, so you could use that to help steer the vehicle. In terms of parallel hybrid, that's much more complex because both the electric motor and the internal combustion engine can drive the wheels. You can imagine the transmission has to be quite sophisticated and complex in order to deal with the torque switching over between both of those drives and ensuring that there's no damage as a result of that. In terms of a series hybrid, at high speeds the efficiency can be lower, and the reason for this is that you're basically running the engine to produce electricity to power the motor to drive the vehicle. So you've got two sets of losses. You're burning your fuel in the engine where there's losses, and you're using that through the motor, and there's additional losses there to drive the vehicle. Whereas in a parallel hybrid, at higher speeds, you can drive the vehicle from the engine alone, so you've only got one set of losses. So the speeds and torques can be chosen independently, and you can get more efficiency across a wider range of speeds and loads. In terms of a series hybrid, you need a smaller internal combustion engine and a larger electric motor. Obviously the IC engine is just run as a genset, so it doesn't need to be large. It's not generating any torque for to drive the vehicle, but you do need a larger electric motor. And it's kind of vice versa for the parallel hybrid. You need a smaller electric motor, or smaller electric motor is required, and you can have a larger internal combustion engine. And kind of ultimately, this means that the series hybrid is better predominantly for urban driving, whereas a parallel is kind of better for general purpose driving, where you need the internal combustion engine on highways and things like that, motorways. So this is a typical hybrid operation. Now, as you can imagine, the manufacturers are fairly secretive in the way that they manage the power going to the wheels, and obviously they put a lot of money and investment into getting that right, because it's quite critical for the vehicle. But typically this is how you could expect it to operate. So in terms of launching the vehicle from the start line, or when you're pulling away, the electric motor is better for that. Electric motors have a lot of low-end torque, and so you use that to pull away, and you don't need the internal combustion engine. For gentle acceleration, so I should have said, this is basically the energy that's being used. Electric is in red, and internal combustion engine is blue. And you notice this line here is a zero line, so if it's above the line, you're using that energy, and if it's below the line, you're recovering that energy. Okay, so use electric motor to pull away. Gentle acceleration, probably use the internal combustion engine to accelerate up there. Cruising at relatively high speeds, again, we'd have the internal combustion engine on and potentially be charging the electric motor as well as we're going. Then if you needed full acceleration or high load, you could switch the motor on for power assist, so to overtake, or as I say, go up quite a steep hill. You can use both the engine and the electric motor to help you do that. When you're decelerating, obviously you don't want the engine on, you're just wasting fuel, but you can have the electric motor regenerative braking, so recovering that energy, and then obviously when it's stopped, you can have them both off. And so, as I say, the way that this is managed is quite complex and quite interesting, I think, in how you can optimize how's best is when to use either electric engine or the internal combustion engine, which scenarios is best for what optimal power usage. So talked about the actual energy sources, and we talked about in terms of hybridization. So far, just talked about batteries, but there are other ways that you can create a hybrid vehicle apart from batteries. You can use flywheels, fuel cells, capacitors. These are all being talked about, but again, you still have the same problem. So as with my earlier plot I had, basically got energy density here, so this is in joules per kilogram, and power density, so this is watts per kilogram. And again, our incumbent technologies, our internal combustion engine, have very good energy density, so they'll have a lot of energy per kilogram, and you can access it very quickly, so they have huge power densities. And when we start looking at some of the other technologies, so let's take, for example, a supercapacitor. So in terms of a capacitor, they have huge amounts of power, and you can access that. So you can access the energy very quickly, but you can't store very much. And vice versa with a fuel cell. Okay, you can store lots of energy, but you can't extract it very quickly. So that's a bit of an issue. And batteries are kind of almost the worst of both worlds. I mean, they're getting better, obviously, but still kind of maintain that the incumbent technologies are still quite hard to beat when you're comparing like for like. So we've kind of talked about hybrids up to now, and kind of extrapolating this to full electrics. I mean, I don't know if this is a good example or not, but using the example of motorsport, you perhaps know that Formula 1 is now a hybrid formula, and so there's an electric powertrain on here as well as the internal combustion engine. And just to give you an idea, this Lewis Hamilton's Mercedes will do the Brazilian Grand Prix, which is 300 kilometres in an hour and a half. So that gives him an average speed of around 126 miles per hour, and he'll do it on 100 kilograms of fuel. Just by contrast, the FIA have got another category called Formula E, and for example, the Morocco Grand Prix, which is 98 kilometres, so it's a third of the race distance. That does that in the winner of that did that in just over 3/4 of an hour. So the average speed was much less, and they're kind of limited to this 175 kilowatts. And the reason I've shown two vehicles here is because currently the drivers have to switch cars halfway through the race. So because the energy is depleted, because the batteries don't have the energy capacity to go the whole race distance, the driver actually has to pull into the pits after about 16 laps, change vehicles, then go back out again. So just kind of illustrating really the issues you've got going from a hybrid system to a full electric system in terms of the energy capacity of the or the energy density of the batteries, that they're just not there yet to go the kind of ranges that we want or that we're used to really. So, well, what is the future for automotive? Well, what we're really doing is, if you think about it, you can think about it this way. We're moving from what was historically a mainly mechanical device with some electrical components. And as we improve our energy efficiency, we're moving to basically what's more a mainly electrical device with some mechanical components on it. And so we've got this trend from mechanical platforms to electrical platforms. And this kind of demonstrated, nearly by kind of driverless cars that are currently being developed. And these are kind of termed connected and autonomous vehicles, or CAVs. And the field of CAV is truly an interdisciplinary area, bringing together mechanical engineering, electrical, psychology as well, as a driver, software development, etc., etc. And, this kind of brings many advantages. There's a statistic that 90% of road deaths and injuries are due to human error. And obviously, a computer arguably won't make the same mistakes. So you can not only reduce the road deaths, but you can reduce the impact on congestion. If you have a smart city and you're controlling the vehicles are in sequence with the lights, you can reduce the congestion citywide and reduce CO2 emissions. That then has a knock-on effect onto the air quality and emissions. And in fact, UE is looking at this. We're taking part in a project looking at CAVs. And in particular, the handover between the car and the driver. So when the car's driving along autonomously and it needs to give control back to the driver, what is the response time of the driver? How quickly does the driver get the car back under complete control? And we're looking at that project called Ventura, and there's a link to the site if you want to go and have a look at that. So in terms of CAE development, this is some of the things that we're going to have to start thinking about. So just give you a moment to read this. So hopefully you can read this. Just pause it before I talk over it. But basically it says, according to a researcher at Cambridge University, it doesn't matter in what order the letters are in a word are. The only important thing is that the first and last letter be at the right place. The rest can be a total mess, and you can still read it without a problem. This is because the human mind does not read every letter by itself, but the word as a whole. And it's kind of true. I mean, could you imagine writing a computer code to read that? Your brain just automatically does this. It makes these decisions, but the computational code to kind of read this by brute force would be astronomical. So we need to come up with more, I want to say intelligence, probably not the right word, better ways of programming to ensure that connected autonomous vehicles can make the same sort of decisions that we can without following this hard logic. They need to have this kind of fuzzy logic to be able to look at something and instantly make a decision. So that's what I'm saying. We need this kind of qualitative rather than the rule-based approach to make decisions. And to just kind of put that into context, this is the lines of code in millions. So a F-35 Joint Strike Fighter, that's got 5.7 million lines of code in it. Windows 8 has 20 million lines. Mercedes-Benz already has 60 million lines of code in it. And then the CAV, well, that's kind of predicted to be somewhere between 300 and 3,000 or 3 billion lines of code. So we need a better way of doing this if these really are going to be the future, and help save not just lives but carbon dioxide, help reduce carbon dioxide emissions in the future. Okay, so I hope you found that lecture interesting. Any comments or queries, then let me know. Thanks for listening.